The National Electrical Code, or NEC, is widely used in Latin America as a reference for electrical safety requirements. It provides comprehensive information on electrical wiring, equipment installation, and safety standards. Chapters 9, 10, and 11 cover voltage drop calculations, power factor, and discrimination respectively. Electrical Calculations, a step-by-step guide by Ed Stavely, provides clear and concise explanations of electrical calculations, including wire sizing, voltage drop, and power factor. The Power Factor Correction Handbook by Roger C. Dugan focuses on the calculation and improvement of power factor, with detailed explanations and case studies. The Electrical Discrimination Handbook by Douglas C. Olszewski covers the principles and practices of electrical discrimination, including coordination studies and relay settings. The NEC is available in Spanish and English in most countries in Latin America. The other books may be harder to find, but can be purchased online from international retailers. IE 141, the Red Book, is a recommended practice for electrical power distribution for industrial and commercial buildings. ANSI/NFPA 70E, the standard for electrical safety in the workplace, provides guidelines for electrical safety in workplaces. IEC 60364 is an international standard for electrical installations in buildings. Electrical codes and standards may vary slightly between different countries in Latin America. It is important to consult with local authorities or electrical professionals to ensure compliance with the applicable regulations. Calculating cable sizes involves several factors, including the ampacity of the conductors, the voltage drop, and the ambient temperature. The NEC provides tables and guidelines for determining the appropriate cable size for a given application. Firstly, determine the load current. Calculate the total current that the cable will need to carry. This is based on the power requirements of the equipment or devices that the cable will supply. Secondly, select the appropriate ampacity. The ampacity of a conductor is its current carrying capacity, expressed in amps. The NEC provides tables that list the ampacities of various conductors based on their size, insulation type, and installation conditions. Refer to NEC Table 310.15b16 for ampacity ratings of insulated conductors rated up to 2000 volts. Thirdly, correct for ambient temperature. The ampacity of a conductor decreases as the ambient temperature increases. If the ambient temperature is higher than the temperature listed in the NEC tables, you will need to apply a correction factor. The NEC provides correction factors in Table 310.15b2. Fourthly, correct for the number of conductors in a raceway or cable. When multiple conductors are installed in the same raceway or cable, their ampacity must be reduced to account for the increased heat generated. The NEC provides adjustment factors in Table 310.15. Fifthly, calculate the voltage drop. Voltage drop is the decrease in voltage that occurs along a cable due to its resistance. Excessive voltage drop can cause equipment to malfunction. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Use the following formula to calculate voltage drop. Voltage drop equals 2 times K times L times I divided by circular mils, where K is the direct current resistance for the conductor material, typically 12.9 ohms for copper and 21.2 ohms for aluminum. L is the length of the cable in feet, I is the current in amps, and circular mils is the cross-sectional area of the conductor. Sixthly, select the final cable size. Based on the calculations above, select the cable size that meets the ampacity requirements and limits the voltage drop to acceptable levels. It is always better to choose a slightly larger cable size than necessary to provide a margin of safety. Understanding and calculating power factor is crucial for efficient electrical system design and operation. Power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. It represents how effectively electrical power is being used. A power factor of 1 indicates that all the power is being used effectively, while a power factor less than 1 indicates that some power is being wasted. The formula for power factor is power factor equals real power divided by apparent power. Power factor is also equal to the cosine of the angle between the voltage and current waveforms. Power factor can be leading or lagging. Leading power factor occurs when the current leads the voltage, typically in capacitive circuits. Lagging power factor occurs when the current lags the voltage, typically in inductive circuits. Low power factor can cause several problems, including increased energy costs, reduced equipment capacity, and voltage drop. Utilities often charge penalties for low power factor. Power factor can be improved by adding power factor correction capacitors to the electrical system. These capacitors supply reactive power, which reduces the amount of reactive power that the utility must supply. Determine the existing power factor. Measure the real power, kilowatts, and apparent power, kilovolt amps, of the electrical system. Calculate the existing power factor using the formula power factor equals real power divided by apparent power. Determine the target power factor. Decide what power factor you want to achieve. A common target is 0.95 or higher. Calculate the required kilovolt amps reactive. Use the following formula to calculate the amount of reactive power needed. Kilovolt amps reactive equals kilowatts times the tangent of the angle of the existing power factor minus the tangent of the angle of the target power factor. Select the appropriate capacitor size. Choose capacitors that can supply the required kilovolt amps reactive. Capacitors are typically rated in kilovolt amps reactive. Install the capacitors. Connect the capacitors to the electrical system at appropriate locations. Common locations include at the main service entrance, at individual loads, or at distribution panels. Discrimination, also known as selective coordination, is the process of ensuring that only the circuit breaker or fuse closest to a fault opens, while the upstream devices remain closed. This minimizes the extent of the outage and allows the rest of the electrical system to continue operating. Discrimination is essential for maintaining a reliable and safe electrical system. Firstly, perform a coordination study. A coordination study is a detailed analysis of the electrical system that identifies potential fault current and determines the appropriate settings for the overcurrent protective devices. The study should be performed by a qualified electrical engineer. Secondly, determine the fault current at each point in the system. Calculate the maximum and minimum fault currents that can occur at each point in the electrical system. This information is needed to select the appropriate overcurrent protective devices and their settings. Thirdly, select the overcurrent protective devices. Choose circuit breakers or fuses that have appropriate interrupting ratings and time current characteristics. The interrupting rating is the maximum fault current that the device can safely interrupt. The time current characteristic is the relationship between the current flowing through the device and the time it takes to trip. Fourthly, set the overcurrent protective devices. Adjust the settings of the circuit breakers or fuses to ensure that they will trip selectively. The settings should be based on the results of the coordination study. Fifthly, verify the coordination. Test the electrical system to verify that the overcurrent protective devices are coordinated properly. This can be done by injecting a simulated fault current into the system and observing which devices trip. The NEC provides guidelines for discrimination in Article 240. It requires that overcurrent protective devices be selected and coordinated to provide adequate protection for the electrical system.